Okay. Okay, so if there are no other questions, let me.
So one more.
Yeah, tell me.
Yeah. So what about this example? Suppose we are taking x square in qx. So we can write it as x by 2 times 2x. X by 2 is in qx and 2x is also in qx. But yeah, so now we want from this like product of irreducibles in qx, we want to have a product of irreducibles in zx.
So,
But
what is your example again?
we are writing x square as x by 2 times 2x.
X square as x by 2 times 2x. Yeah.
Yeah. So now when we want to, like, suppose this is capital G, small g times small f, and we want to have the capital G and capital F from this representation. So in that case, for 2x, we can't have any element in R such that that element times 2x is a polynomial in ZX.
I see.
So the problem is that when you clear out the denominators, that time the G and S that we get may not actually
It's not,
Yes, yes,
yeah,
yeah.
it's not the original G and H. Yeah, once we clear
Yes.
out the denominator, that's right.
But I think it should be true if like F is primitive or something. But without that as an option, it can.
Yeah, you're right. So maybe I should do this correction. Yeah. So let's get back to this. Yeah, so I can only conclude that they are in K because we are after clearing the denominators, it's okay, but not before that. Yeah. So let me get. Yeah, but I mean, we didn't really, we only used that they are associate in KX. Yeah, we didn't really use it in. Okay. I'll fix this in notes as well. Yeah, this is the notes I've shared. Any other? Yeah, so now this is okay. Yeah, so after clearing the denominator, only this. Yeah, that's right. So yeah, this looks okay. Okay. Anything else? Yeah, thanks for this this correction. Yeah. Anything else? Okay, so if there are no more queries or comments, let me just yeah, what did I do? Okay, so let me begin this lecture now. So last time we talked about Noetherian rings. So maybe this is recall. Yeah. So we saw that ring is. So we saw the definition of Noetherian ring, which was that a ring is Noetherian if any of these equivalent condition holds. That is, every ideal is finitely generated, or every increasing chain of our ideals become eventually constant, or every non-empty collection of our ideals has a maximal element with respect to inclusion. Okay. And then we saw some examples of Noetherian ring, which was fields and PID, and then I stated this result that R is Noetherian implies Rx is Noetherian. So this is called Hilbert basis theorem. So we'll see a proof of this today. Okay, and then the other facts which are not difficult to see. So yeah, maybe we'll begin by, so we didn't see a proof of these facts, that localization of a Noetherian ring is Noetherian, and if you have R is Noetherian, then R mod I is Noetherian. So they are easy to see results. And if R1 to Rn are Noetherian, then R1 times R, then their product is Noetherian. So the last one I won't tell you, it's sort of straightforward as well, but and not very, anyway, this is not quite not that useful. But anyway, I mean, it's also not difficult, but these two are very useful. So maybe I'll show you all three. Yeah, and then we'll move on to the main theorem, which is R is Noetherian implies Rx is Noetherian. So Hilbert basis theorem. Okay. So let's see. I mean, localization, it just, these things just comes out by looking at how the ideals behave, yeah? So, maybe write it in black. So let R be a Noetherian ring, and S be a multiplicative subset of R. Then we want to show that S inverse R is Noetherian. Yeah, so let I contained in S inverse R be an S inverse R ideal. Yeah. So in fact, we know that I is going to be S inverse of something. Yeah, S inverse of Phi inverse I, where P is the natural map from R to S inverse I. Yeah, but in particular, it's going to be S inverse of some ideal. Yeah, so by what we have seen, we know that I is S inverse J, where J equals Phi inverse I is an R ideal. And Phi is the map, R is the natural map, yeah? Localization map, R to S inverse R going to R over 1. Yeah. But J is, since R is Noetherian, J is finitely generated. But R is Noetherian implies there exists x1 to xn in J such that J equals x1 to xn. Yeah. Then my claim is that I is so S inverse J means it looks like is the ideal generated by elements of J. Yeah, so it's actually going to be, so claim is that I is generated by x1 over 1 to xn over 1 in S inverse J, in S inverse R. So of course, how does an element of I look like? It's S inverse J, so it looks like, so if alpha belongs to I, then alpha equals x over S for some x in J and S in R. Yeah. This is what we saw S inverse J looks like. Yeah, so it's some numerator is going to be an element of the ideal J, and denominator is going to be some element of S. Yeah, which implies, but X is in J implies that X we can write it as some R linear combination of X1 to Xn. So X equals, so maybe this is not implies, but X equals R1 X1 to Rn Xn, R1 to Rn in R. Yeah, so which implies alpha, which is X over S, is equal to R1 over S, X1 over 1 plus Rn over S, Xn over 1. Yeah. And note Ri over S belongs to S inverse R for all I between 1 and. Yeah, so this shows that hence I is finitely generated. Hence the claim, and from there we get that R is Noetherian. In particular, S inverse R is not. Hence, S inverse R is Noetherian. Yeah. So for localization, it still there is some calculation, but for quotient is even more trivial. Yeah. So R Noetherian, and and say some J is contained in R mod I, an ideal of R mod I, where I is an R ideal. Then what do we know about J? Then we know how the ideals in the quotient look like. So then J is equal to some ideal J tilde mod I, where J tilde is an R ideal containing I. Yeah, so there is a bijection between ideals of R mod I and ideals of R containing I. But R Noetherian implies J tilde is finitely generated. J tilde is generated by say X1 to Xn for some Xi's for some X1 to Xn in J tilde. So every ideal is finitely generated, which implies J is generated by, so if J tilde is generated by X1 to Xn, their images will generate J. Yeah. So J is generated by X1 bar to Xn bar. Yeah, or you can think of it as X1 plus I to Xn plus I quotient, if you want to write it in terms of quotients. Yeah. Hence, R mod I is Noetherian. Okay. Similarly, so even in product of rings, so if R is R1 cross Rn, where Ri is a Noetherian, and I is some ideal in R. What do we know about I? How does I look like? What can we say about I?
Product of ideals.
Yeah, so we saw that I is of the form I1 cross In, where Ij in Ij is an ideal. It's product of ideals. And since each of them are finitely generated, the product is finitely generated. Yeah. Since I1 to In are, so say I1 is generated by x1 to x, xi1 to x, yeah, so it will be generated by some bigger set. So you'll have to take all procedural products, but it's okay. Are finitely generated. Hence, I is finitely generated. So, if you want, I can tell you. So, say I1 is generated by, or maybe let me just write it in terms of notation. Say I sub j is generated by xjk. Yeah. K between 1 and nj. Then you just take all possible products. Yeah, so all possible tuples, and then I is, so maybe I'm giving a bigger possible set, but I is generated by xjk j between. Sorry, so I should write it as a tuple. Yeah. Generated by x1 1, I don't know, k1 x2 k2 x n kn. So you consider the set. Yeah, ki is k1 is some number between n1 and so on. So kj is between 1 and nj. So you consider the set. So this, but it is finitely many. Yeah, so it's okay. So you can show that these generate whole of I. Okay. Okay, any questions? Okay. So basically it's component wise addition and multiplication. So that's pretty much we'll seal it. Okay. So I mean, you have you'll have to use idempotence to make sure everything works out. Okay. So this is proving that proving the trivial parts of this statement. That is okay. So I went over the line. Okay. So proving that these last three statement, and the next one is Hilbert basis theorem. Yeah. So we will you'll see the proof of Hilbert basis theorem now. And okay, I hope that this is visible, better visible. Okay, so this will require a little bit of Hilbert basis theorem requires a little bit of work. So we'll prove that, and then we'll move on to other things. So, but note that once we have proved Hilbert basis theorem and these things, then more or less all reasonable rings you construct will be Noetherian. Yeah. So you look at the rings. The way we construct ring is we start with a field or an integers ring of integers and so on. We either do localization or we take polynomial rings or we take quotients. Yeah. In infinitely many variables, and we get new rings. So we'll get mostly Noetherian rings. If you take polynomial ring in infinite, yeah. So maybe one counter example is that if you take polynomial ring in infinitely many variables, so over anything, so maybe Q, x1, x2, so on. Yeah. So the way to think of it is, yeah. So think of this as. So we have done only finitely many polynomial ring in finitely many variables. Yes, but we know that this is and this you can think of it as subring of this guy, xn plus 1. Yeah. So let's call this Rn. So Rn is a subring of Rn plus 1 and so on. So you take R to be union of Rn and greater equal 1. Yeah. So then this will be a ring because I mean, if you take any, so you want to verify all the ring axioms, you take any two elements is going to be in some ring, yeah, some Rn or some n, and hence there's sum and multiplication, etc. All makes sense and all distributive law. So any two polynomial or any finitely many polynomial will involve only finitely many variables. Yeah, so this is okay. But so this is a ring which is not Noetherian. So this you can think of. So this is what polynomial ring in infinitely many variables. Formal definition of polynomial ring in infinitely many variables is. Okay, is a ring which is not Noetherian. And you know what, which ideal is not finitely generated, or which chain of ideals you can take, yeah? X1, then X1, X2, and then X1, X2, X3. This is going to be an ever-increasing chain of ideals. Okay, or you can take the ideal generated by all the Xi's. That's not finitely generated, one way or the other. Okay, so that's example of a non-Noetherian ring. Yes.
So will this remain an UFD over here?
Say that again.
So will this remain a UFD over here?
Yeah, this ring happens to be UFD. This ring's still UFD.
So this is also an example for that case.
Yeah, a non-Noetherian UFD. Yeah, that's right. So UFD need not be Noetherian.
Okay, sir. Yeah? Thank you, sir.
Yeah. So, but yeah, so anyway, they have, yeah, so there are more crazy examples of non-Noetherian ring. This is something somewhat reasonable example of non-Noetherian ring, but technically one can capture this ring in, this is still somewhat well behaved, but once you get out of the Noetherian setup, you can get many crazy rings. Yeah. So, okay, so let's get to Hilbert basis theorem. So let R be a Noetherian ring, then Rx is also Noetherian. So what we'll do is take an ideal in Rx and we'll show that that ideal is finitely generated. Yeah. So how will you do it? If you want, if you are given an ideal in Rx and you want to find a generating set of that ideal, then I mean, you try the natural thing. Yeah, you start with some polynomial and you choose the polynomial of least degree. Yeah, that is how, if you want to build up generating set, this is how you will try, right? So you'll see if there are some constant or not. If there is some constant, you'll see whether that tries and try to generate, consider the ideal generated by that, and then go to the next degree polynomial and so on. Yeah. So let f1x be an element of I. So a non-zero polynomial of the least degree, and let's call that degree n1. Yeah, and consider I1 to be the ideal generated by f1x. So if I1 happens to be I, then we are done. Then I is in fact singly generated. Yeah. Otherwise, you take f2x, which in I minus I1, and now you choose f2x such that it has the least degree. Yeah, so this is how we will build. We'll try to cook up our generating set, and let's say the least degree is n2, and then you consider I2 and so on. Yeah, so this way we can construct. So if you are given up to fi, you can construct fi plus 1 using this method. Yeah, you take fi plus 1 in fi minus in I minus I sub I of least degree, and that degree we call ni plus 1, and then we cook up this new ideal I sub I plus 1 is generated by f1 to fi plus 1. Yeah, so we want to show that this stops. Yeah, so we'll have to find some capital. So if this doesn't stop, then we would have constructed an infinite sequence of fi's. But we will show that this indeed stops. Yeah. So we want to find some capital N which will make it stop. Yeah. And this is where we will use the fact that we are taking polynomials of least degree. Yeah. So consider the leading coefficients of these fi's and call it ai. So let ai be the leading coefficient of fi, and consider this ideal j, which is generated by a1, a2, and so on. Now R is Noetherian tells us that j is in fact finitely generated. Yeah. So we can find an n, capital N, such that, so it will be generated by some ai1 to ain, but we will throw in the intermediate terms as well. Yeah. So assume that j is generated by the first capital N elements. So we can find such an n. Yeah. Because so this is where we are using that R is Noetherian. Okay. So so once we have that j is generated by a1 to an, then the claim is that that I will be generated by f1 to fn. Yeah. So we'll show that you don't get fn plus 1. Okay. And then that will prove that I is finitely generated, and hence we are this ring Rx is Noetherian. Okay, so let's see that claim. Yeah. Okay, maybe I'll minimize this. Okay. So the claim is I is generated by f1 to fn. So suppose not, then the pointers will try. The leading coefficient of fn plus 1 doesn't have much of a choice. Yeah. So it has to be. So we'll be able to decrease the degree of fn plus 1. Yeah. So if not, then fn plus 1 exists, and fn plus 1 is some element of I minus I sub n, where I sub n was the ideal generated by the first n guys. Yeah. So so how does fn plus 1 looks like? It's a sub n plus 1 times x power nn plus 1, where n sub n plus 1, remember, is the degree of fn plus 1. Yeah. Plus lower terms. Yeah. So there will be some lower degree terms. degree terms. Now we know that an plus 1 belongs to a1 to it belongs to j, and which is generated by a1 to an. So we can find elements bi's in R such that an plus 1 is this linear combination of capital A1. Yeah, so an plus 1 is b1 a1 plus b2 a2 up to bn an. Okay, and also what do we know about the degree of fn plus 1? The degree of fn plus 1 is nn plus 1, and this degree has to be greater equal degree of fi for I less than n plus 1. Right? Because note that here, for instance, when we choose f1 of degree n1, then what are we doing? F1 is the least degree, yeah, and f2 also belongs to that set where we are looking at for the least degree. So the degree of f2 is at least the degree of f1. Yeah. So similarly, degree of fn plus 1 is going to be at least the degree of fn, which is going to be at least the degree of fn minus 1, and so on. Yeah. So the degree of these functions increases, meaning is non-decreasing. It can be equal. It may happen that degree of fn plus 1 is same as degree of fn, but it can't go down. Yeah. So now we'll cook up a polynomial which will show is in I minus in, and which has degree less than degree of fn plus 1. So the idea is to just cancel the leading term. Yeah. So you take gx. So gx is going to be fn plus 1 x, and we want to cancel the leading term. Yeah. So how do we cancel the leading term? We take b1 times f1, but we have to make sure that the leading term, the degree of the leading term is n sub n plus 1. Yeah. So we multiply by x power n sub n plus 1 minus n1. Yeah, and f1 has degree n1. Yeah, so the leading term, so the degree of this polynomial is going to be precisely n sub capital N of 1. Yeah. Similarly, this b2 times this guy has degree precisely n sub n plus 1, n sub capital N plus 1, and the leading term of this thing is going to be b2 times a2, and so on. Yeah. So so we get gx, and we see that gx is going to so the leading term of gx will so the coefficient of x power n sub n plus 1 in gx will cancel out, and gx will be a polynomial of degree strictly less than n sub n plus 1. Yeah. Also, each of these polynomial f1, f2 up to fn plus 1, they are all in I. Yeah. So gx of course is also in I, and note that f1 to fn is in in, but fn plus 1 is not in in. So gx cannot be in in. Yeah. If gx were in in, then of course fn plus 1, f sub n plus 1 will be also in in. Yeah, so what we get is gx belongs to I minus minus in, I can write. Yeah. So gx belongs to I minus in, and in plus 1, not in. So I've already written it down. So let me not write this again. Yeah. So gx belongs to I minus in plus 1, and we observe that degree of gx is strictly less than the degree of fn plus 1, and this contradicts the choice of fn plus 1. So we had chosen fn plus 1 to be an element of I minus in, and it should be of least degree. But gx is an element of I minus in and has degree strictly less than fn. So, and the contradiction occurred from the assumption that fn plus 1 exists, or I is not generated by f1 to fn. Yeah. So hence we get the claim, and we can conclude that R is Noetherian. Okay. Any questions? On Hilbert basis theorem?
Sir, not on the basis theorem, but the fact too that if R is Noetherian and then R mod I is Noetherian,
Yeah.
using that and the basis theorem, can we say that R is Noetherian if and only if Rx is Noetherian? Because if we quotient Rx by the ideal generated by X,
Yeah, sure.
Rx is Noetherian.
Yeah, that's right. So if R is Noetherian implies I'm sorry, Rx is Noetherian implies R mod implies R is Noetherian. Yeah. So, yeah. So maybe one can remark that. So note. So this completes this proof and note R. I don't know why it's coming out multicolored. Okay. Note X is Noetherian implies R is Noetherian. Yeah, because R is just Rx mod, the ideal generated by X. Yeah, but subbing of a, so maybe caution, subbing of a Noetherian ring need not be Noetherian. Yeah. Subring. So maybe this I can write it in red. Important. Subring of Noetherian need not be Noetherian. So, I mean, you shouldn't think Rx is Noetherian and R is a subring, that's why it's Noetherian, because it's a quotient of Rx, that's why it's Noetherian, yeah? What is an example? Example of a Noetherian ring whose subring is not Noetherian.
So, will R and Q work?
Both are Noetherian.
No,
R is
yes, a subset of Q, maybe something like that.
subs.
Not a field, basically like that one half containing half the maximal ring or subring.
Yeah, so see, the point is fields are Noetherian, right? Because fields are PID. Yeah, so you take maybe C or R, anything, yeah, it doesn't matter, R or C. So maybe yeah, let's just stick to C or R, it doesn't matter. Yeah, and then you want to cook up a subring of C, which is not Noetherian. Okay, so how do you do that? Yeah, so maybe you start with Q or Z. Yeah, doesn't matter. And what can you throw in?
Like root 2, then fourth root of 2, and so on.
Yeah, so you can do that, but that will require a lot of maybe. Yeah, so that will require some Galois theory or something,
Yes,
or some field theory. But if you are willing to assume that
transcendentality of
transcendent, yeah. So the point is, so that will require some analytic methods. But anyway, the point is, if I take there are many elements in C which are not. So, for instance, there is an element in C which is not algebraic over Q. Yeah, so which does not satisfy any algebraic equation like pi, yeah, or E. So but let's just say pi, yeah. So Q pi is a subring of C, and we know that Q pi is isomorphic to Qx, polynomial ring in one variable. Now, so pi was just an example, but this q pi is going to be a countable set, yeah. And if I take anything which satisfies some polynomial equation, the set of elements which satisfy a polynomial equation, they are all countable. Okay, so again over q pi, there is another element of C which will not satisfy any polynomial equation with coefficient in this countable ring. Okay, so you can take another transcendental guy, which we'll name T2. So maybe this one was T1. And again, you consider a polynomial ring over T1 and T2. This is again countable and is contained in C. And again, by the same argument, you can say that there exists an element of C, which does not satisfy any polynomial equation. Yeah? As soon as you have such an element, then if you adjoin it, then you get a bigger ring. Yeah, and so on. So this you can do it forever, because the cardinality is always going to be countable here, and this is uncountable. Yeah. So continue this way. Continue this way to construct Q T1, T2, and so on in C. So such that and note that these are isomorphic to polynomial rings. Yeah? So T1 is a polynomial, is isomorphic to a polynomial ring in one variable. T1, T2 is isomorphic to a polynomial ring over T1 in one variable. So T1, T2 will be polynomial ring. So, or more generally, Ti is isomorphic to polynomial ring in I number of variables. Yeah. So this the subring I have chosen is going to be, so this, let's call this R. R is isomorphic to polynomial ring in infinitely many variables. Yeah. Okay, so this is not Noetherian, and of course it's a subring of C, which is a field and hence Noetherian. Yeah. Or another way to think about it is you can do the same thing here. So this you can prove that R is an integral domain here, the ring which we constructed. Yeah, because I mean you can't multiply each of these things are each of these Rn's are no integral domain. So their union is also an integral domain. So since R is an integral domain, you can write down as fraction field, and R will be contained in the fraction field. So R is Noetherian, but the fraction fields are not. Sorry, R is not Noetherian, but fields are Noetherian. Yeah, so that is another way of looking at it. Okay, so subrings have no hope of being Noetherians in general, yeah, because of this kind of thing. You can always make a big field and so on. Okay, any other questions or comments? Okay. Okay, so if there are no comments, maybe we'll take a break, 5-6 minutes. Yes.
So over here, the T2 is defined to have no, is not the root of any polynomial over Qt1.
Yeah, that's right. Yes.
Sir, so second, okay, so it's countable. Are we using countable basis over here by any chance to prove this?
Yeah, so if you take a countable ring and you consider the polynomial ring over a countable ring, then it's trace countable. Yeah,
yes, sir.
That is what we are using.
Okay, sir.
Okay.
Thank you, sir.
Yeah. And if this looks more complicated, you can always go to this example. Okay. But you can find subrings of C which are non-Noetherian. So this is what will prove. Okay, you can in fact find subrings of so I mean you can do it algebraically as well, but that requires a little more work. So I don't want to get into that. Yeah. So once you do field theory, you will realize that you don't. I mean, you can find a countable non-Noetherian ring as well. Okay. Any other question or comments? Okay, so let's take a 5 minutes break. So maybe we'll meet at 12:10. Okay, and then continue. We'll start discussion on modules and so on.